Hi everyone, welcome back. Today we are discussing the properties of liquid helium and the application of Bose-Einstein condensation to liquid helium. So liquid helium as we know, the second element in our periodic table, which has two isotopes, that is helium 4 and helium 3. Two isotopes. Of these two isotopes, helium 4 is the abundant isotope, and the number of particles, that is 2 protons, 2 electrons and 2 neutrons. So it has a zero spin angular momentum. So it belongs to boson. That is helium 4 is boson. But here it has half integral spin. 2 protons, 2 electrons and 1 neutron. So half integral spin. It belongs to fermions. Right. So in nature, helium exists as a mixture of bosons and fermions. Okay. Not only that, helium is the only element which exists in liquid state even at very, very low temperature. Even at less than 5 Kelvin, helium exists as liquid. Right? So we are discussing the strange properties of helium at low temperature and the application of Bose-Einstein condensation. So liquid helium, it is discovered or liquefied in 1908 by Kamerlingh-Onnes. Kamerlingh-Onnes, you all know who is Kamerlingh-Onnes. The name, very famous name related to superconductivity. So in 1908, Kamerlingh-Onnes succeeded in liquefying gaseous helium at 2.2 Kelvin. So at 2.2 Kelvin, gaseous helium is converted to liquid helium. Then at very low temperatures, liquid helium shows some strange properties. So we can discuss in detail. That is, at atmospheric pressure, helium condenses at 4.2 Kelvin, which is the boiling point of helium. At 4.2 Kelvin to liquid helium with a low density, a density of 0.124 gram per centimeter cube. That is density of liquid helium at this temperature, or density of liquid helium. Right? So the condensation starts at 4.2 Kelvin. Actually, below this temperature, condensation happens, and the critical temperature of helium, that is Tc, which is equal to 5.2 Kelvin. Critical temperature. We know what is critical temperature. And critical pressure, which is equal to 2.264 atmosphere. So below this temperature, we can liquefy helium. So at 4.2 Kelvin, helium condenses to form a liquid with a very low density. Suppose we are again cooling liquid helium to lower temperature, right? Even we are again lowering the temperature. Even at 0.82 Kelvin, it remains as liquid. We expect that again we are lowering the temperature, we are cooling, it may convert it to solid form, but it does not freeze. It does not freeze even at this temperature. Does not freeze even at this temperature. It is so believe that it remains as liquid. Helium remains as liquid even at absolute zero, or remain as liquid as down to absolute zero. Okay. So even at this or very near to absolute zero itself, it is a liquid. So it is believed that even at absolute zero, it remains as liquid. All the way down to absolute zero, we can say all the way down to absolute zero, it remains as liquid. Then 3. Alright. As we discussed here, when we decrease the temperature at 2.17 Kelvin, so decreasing the temperature at 2.17 Kelvin, a most strange behavior happens. That is, it shows superfluidity. Superfluidity. Below this temperature, at this temperature or below this temperature, superfluidity happens. That is, helium shows superfluidity. The superfluidity is the frictionless motion or frictionless flow of a liquid. Frictionless flow of a liquid. And in 1938, Capita, Allen and Meissner. This person, Meissner, all of you know who is Meissner effect and everything. So these three persons, these three scientists discovered superfluidity in 1938. Below this or at this 2.17 Kelvin, right? Now helium has two phases. That is helium 4 and helium 4.1 and helium 4.2. Helium 4 first phase and helium 4 second phase. At 2.17 Kelvin, a phase transition happens. That is, at 2.17 Kelvin, helium 1 is converted to helium 2. Above that temperature, helium 2 is converted to helium 1. So that is a transition temperature. Or a phase transition occur. Helium phase 1 converted to helium phase 2. And the properties of helium 1, it is just as a normal liquid. But the properties of helium 2, phase 2, it is superfluid. So helium for phase 2 is a superfluid. Right. This transition is generally known as lambda transition. We'll discuss later why the name lambda comes. And the temperature of transition is known as lambda transition temperature or simply lambda temperature. And is denoted as T lambda. Lambda temperature is denoted as T lambda. So, transition of helium phase 1 to helium phase 2 is known as lambda transition, and the temperature at which this transition happens is known as lambda temperature. So, the lambda temperature is T lambda is 2.17 Kelvin. 2.17 Kelvin. And we can draw the phase diagram of this liquid helium. Phase diagram of helium. X-axis temperature. Temperature in Kelvin, and y-axis is we can say just take it as 10, 20, 30 simply. So in y-axis is pressure in atmosphere. At 2.17 Kelvin, a transition occurs, and as the temperature increases, and reaches at 5.2 Kelvin, this temperature, helium exists as gas. 5.2 Kelvin and 2.264 atmospheric pressure. At this, that is 2.264 atmospheric pressure. This pressure 2.264 atmosphere and 5.2. That is its critical temperature and critical pressure. So, at its critical temperature and pressure, it exists as a gas. Above this temperature, it exists as gas. Okay. Then we discussed that even at low temperature, helium exists as liquid at atmospheric pressure. So, in order to convert this helium liquid into helium solid, we have to apply very high pressure. So, helium remains as liquid helium unless we are applying a pressure of 25 atmosphere. 25 AT. At 25 or above atmospheric pressure, helium exists as solid. So, this is our 2.17 Kelvin. 2.17 Kelvin. That means this is the lambda point. This is our lambda point. 2.17 Kelvin is our lambda point, and this line is known as lambda line. That means where lambda transition take place. Above this temperature, as we told, it is helium 1, that is liquid helium phase 1, and below this 2.17 Kelvin, it is helium phase 2, that is super fluid. That is superfluid. Okay. And this line, this is known as lambda line or transition line. And there is a triple point here, 1.7 Kelvin and 29.8 atmosphere. Triple point, that is a solid and two liquid phases exist. Looking at the phase diagram, we can see that a solid form, a gaseous form, two liquid forms. One liquid form and another superfluid form. This is another state of matter actually. And the state of matter. So, helium, the phase diagram of helium consists of four phases actually. You are very familiar with the three phases, solid, liquid and gas. Here solid, liquid and gas, and in addition to that, a superfluid phase is also there. So, totally there are four phases. As the temperature decreases, below 4.2 it become, or below, we can say below 5.2 Kelvin at critical temperature, below critical temperature, it become liquid, right? And below 2.17 Kelvin it become, again we are cooling, and below this 2.17 Kelvin it become superfluid, right? And if we are applying very high pressure at low temperature like this 1.7 Kelvin, we can convert it into solid form. This is the phase diagram of liquid helium. Sorry, phase diagram of helium. And when it becomes liquid, or we can say at 2 point or below 2.17 Kelvin or below T lambda, helium shows strange properties because viscosity tends to 0. Viscosity of liquid helium tends to 0 below lambda temperature, that is below 2.17 Kelvin. Then it becomes, that is frictional force is equal to 0. Frictional force is equal to 0. So, and hence it's so superfluidity. That is, viscosity is 0, frictional force is 0, so it can flow, that is superfluid property. That is, liquid helium can flow up along the walls of the container which is taken as a thin film and overflow. Right? Suppose we are taking helium in this one, then we can move up like a thin film and overflow. That is a superfluidity. So frictionless flow of liquid, that is superfluidity. Then fourth one, thermal conductivity. Thermal conductivity is high, very high, of the order of 3 into 10 raised to 6. Thermal conductivity of liquid helium is very high, and it is very important in our superconductivity. So thermal conductivity is very high at this low temperature. Then the scientist Hazen determined the heat capacity of liquid helium and found that it is not continuous, or there is a discontinuity in the curve of specific heat of liquid helium. We can draw the curve. Okay, there is a discontinuity in It is again temperature in Kelvin, and it is CV. When first it increase, okay, then there is a discontinuity and curve. Between the curve is like this. Okay, at 2.17, there is a discontinuity in specific heat capacity. There is a discontinuity, and when looking at the curve, just twist it. Twist this one. You get a curve like this. It is equal to our lambda. The shape of the specific heat curve is just like that of lambda, and from that lambda point arises. This lambda point arises. So lambda point arises from this discontinuity, that is at which the specific heat discontinuous. So the shape of the specific heat curve is just like that of lambda. The shape of the curve is just like that of lambda. From that, this lambda point arises. That is lambda temperature. Lambda point means lambda temperature, and the same lambda transition also from this curve. This discontinuity curve, the name obtained. Okay, so at 2.17 Kelvin, that is lambda point, what happened is that most of the helium atoms occupy ground state. Most of the helium atom occupies ground state. That means ground state population increases. And we know from our Bose-Einstein condensation, TB or T0, you can write as T0, that is Bose temperature or condensation temperature, which is equal to h square by 2 pi m k into n divided by v into 2.612 whole raised to 2 by 3. This 2.612, the value of B is set, or in some cases it is written as S function. It is obtained from Riemann-Zeta function, and the value is 2.612. It is already discussed in detail in our Bose-Einstein condensation. When we are applying the value of molar volume for helium, we get a value 3.12 Kelvin. 3.12 Kelvin, that is TB or T0 or TB is equal to, some text it is given as T0. Remember, same. T0 is the same as Bose temperature or condensation temperature. Okay. So which is equal to 3.12 Kelvin. We are substituting the value of V. N is the total number, 1 mole of substance. So this 2.17 Kelvin and 3.12 Kelvin, they are very close to each other, right? This is our T or T lambda. And from our equation, that is again from Bose-Einstein condensation, N0, that is population of ground state or total number of particles present in ground state, which is equal to N into 1 minus T divided by TB or T0. When T is less than TB, that is the temperature T at which the system exists is less than TB, what happens? Most of the particles exist in ground state. When T approaches 0, that is absolute 0, N0 equal to N. Again, we discussed all these things in our Bose-Einstein condensation. When T is equal to T0, then N0 is equal to N. That is, all the particles occupy ground state. When T is less than TB, and most of the particles start to occupy ground state. So here, just look at the temperature. So at this temperature, most of the atoms of helium occupies ground state, and that is what is known as Bose-Einstein condensation. So the conversion of helium phase 1 to helium phase 2, that is conversion of normal liquid helium to superfluid liquid helium, is due to Bose-Einstein condensation. At that lower temperature. Not only that, at this temperature, entropy of the system is getting increased. It is true as given by Bose-Einstein condensation and approaches zero at absolute zero. The entropy becomes zero at absolute zero. So again, satisfying the suggestions given by Bose-Einstein condensation. But in the case of He3, it is a fermion. It does not undergo, or even at 2.17 K, it does not show superfluidity. But again, we are decreasing the temperature at very low temperature, 0.08 Kelvin. It shows superfluidity because two helium atoms coupled undergo coupling, or you can say undergo pairing. Two helium atoms undergo pairing. So it exists as pairs. When it exists as pairs, when particle exists as pairs, two atoms undergo pairing and exist as single particle, what happen? Now it is a half integral spin particle, right? When it undergo pairing, it becomes zero integral, okay, or integral spin. That means on pairing, this fermion, that is helium-3 is a fermion. On pairing, this fermion is converted to boson actually. At very low temperature, undergo pairing, or helium-3 exists as pairs, and due to the pairing, it is converted to boson. Boson converted means its integral value, that is spin angular moment value changes and behaves as boson. We can say it behaves as boson at very low temperature. When it behaves as boson, it undergo Bose-Einstein condensation and shows the property of superfluidity. And the pair, it is known as Cooper pair. It is the Cooper pair. The pairing of this, the pair obtained at very low temperature. That is, two atoms pair, exist as a pair and behave like that of boson. And that pair is known as Cooper pair. So it shows superfluidity at very low temperature. Then why liquid helium or helium phase 2 shows superfluid character? And again, one more thing, that London suggested that liquid helium phase 2 is equal to a Bose gas. So it obeys Bose-Einstein statistics and undergo Bose-Einstein condensation at lower temperature. Why this shows superfluidity? Because weak interaction between the atoms. We know helium is a noble gas. There is no interaction between them. So each atom can move without the influence of other atoms. Then mass, that is small mass of helium Small mass of helium also is a reason for superfluidity, right? As the mass decreases, the mobility increases, so without any influence, it can move. So it cannot condense further to solid phase. Then 3, the transport properties. Transport properties, we know what are transport properties, such as thermal conductivity, viscosity, diffusion, etc. of helium, liquid helium, is just same as that of an ideal Bose gas. The transport properties of liquid helium is just as same as that of an ideal Bose gas. If it is just like that of an ideal Bose gas undergo Bose-Einstein condensation, so it undergo condensation. Then the molar volume is very high at this very low temperature. The molar volume is very high, very higher than that calculated. 3 times higher than that calculated. So as the volume increases, interaction again decreases, so it can move its own. So these are the reasons why helium behaves strange or shows strange behavior at a very low temperature. So we discussed the application of Bose-Einstein condensation and some of the behaviors. We are not going to London's theory in detail, and Landau's theory is so we are not going to that. Just the application of Bose-Einstein condensation to liquid helium. Thank you for watching.